In today's video, here is a nice problem that what exists by view. Here is the following information. Find all primes p and q such that we have this following setup. We have p square plus pq plus q is a multiple of p plus q. So all of these are primes, okay? In fact, this is very simple and quicker problem to solve if you look at this problem on the evenest side, okay? Now let's jump into solution. Since we have a kind of symmetry here, so I'm going to work on this order. Let's assume p is smaller than q, and you can do the inverse, q smaller than p. So without loss of generality, let's assume 2 is inferior to p and p is inferior to q, okay? So let's take the base case when we have equality in even primes. So if p equals q equals 2, this is the base case. Let's replace everything into this setup. So we are saying this one is a multiple of this one, which means this one equals a sum integers is multiplied by this one, okay? Let's replace this value of 2 into each prime, okay? So we get p square, which is 2 square, plus 2 is multiplied by 2. If I'm going to calculate this one, you get 4 here, 4 here, 4 here, which is 12. 12 is going to be written on the form of 3 factor 2 plus 2. So it's more simple. We determine the solution for this equation. If you are taking p equals to this one and q equals this one, this is p, this is q. So here is the first obvious solution. We get p equals 2 with q2. Now let's assume if p equals 2 but q is odd, okay? Well, let's simply replace this number 2 into here, into p here. So we get q squared plus 2q plus number 4, which equals k is multiplied by p plus q. P is going to be replaced with number 2 plus q. Now we get the form quadratic polynomial. I'm going to put this one on the form of the quaternary square. So it's more simple. It's going to give us q plus 2 quaternary square. If I'm going to distribute this one out, I get q square, which is good. I get here 4q, which is not good because we get 4 times q. So we need to subtract minus 2q from here. Plus the original number 4, which is good, which equals k factor 2 plus q. So I'm going to add 0 here by adding number 4 minus 4. So we get minus 4 here plus number 4. Then I'm going to take minus 2 as a common factor for these two terms. We get minus 2q and minus 4. So I get q plus 2 quaternary square minus 2 factor q plus 2 plus an extra 4, which equals k factor 2 plus q. So since we get to this expression and we get q plus 2 in each term, okay, except this one. So since we get q plus 2 is positive, I'm going to divide the whole thing by q plus 2. I get the following. I get q plus 2, which means this one was simplified to q plus 2 after dividing by q plus 2. This one become more simple minus number 2 here, plus number 4 is divided by q plus 2, which equals k after you simplify it, after dividing this one by 2 plus q, okay? So we get cancelled out this number 2, so which means I get q plus 4 all divided by q plus 2, which equals k, okay? So since we get q is a natural number, okay, which means the left hand side of this equation must be a natural number as well. So q is a natural number, this one also is a natural number, which means since we get number 4 in numerator, which means this q plus 2 is going to be 1 or 2 or 4. It cannot be number 1 because we have q here is superior equal to 3. We cannot be 2 because it cannot be 2 because we already have number 2 here, which means it's going to be 4, okay? This one immediately is telling us that q plus 2 divides 4, is telling us q plus 2 is going to be 4. Okay, thus q equals 2. If q equals 2, it's impossible. What we have contradicted, we have contradicted our assumption, because we assumed q must be odd, but we found q is even, which is impossible, which means p and q cannot have different parity, which is impossible to have this one on this form, which means both of them, p and q, are odd. Okay, since we have proven that, we are going to change this assumption into like 3. Okay, now we have done with the evenness, we are going to move on to the oddness. Maybe we have equality in p and q if they are odd. We are going to check that before we move on to the last case. Okay, so we have equality in p and q if p equals q. I'm going to put this one in terms of the other one, so I get here p squared plus p squared plus p squared, which equals 3p squared. Okay, so which equals a multiple of p plus q, which is 2 times p. Okay, since we get p here, p is different than 0, I'm going to divide both sides by p, so I will be ended with 3p, which equals 2 times k. But remember here, this one, it was odd, which means the left hand of this equation must be odd, but this one is even, which is impossible to be like this. Okay, which means we cannot have any equality in p and q, since we find this contradiction. Okay, so which means p and q are both odd, and always they are not equal to each other. So we are going to fix this inequality into straight inequality like this. Now this is the assumption we are going to work on. Okay, now let's get rid of this one and move on to the general case. This general case is going to be more quicker if we look at evenness and oddness of this expression. So let's take a look at this. We have p squared plus pq plus q squared, which equals k is multiplied by p plus q. Okay, if you take a look carefully at this sum, since both are odd, which means if you sum them, you will get even. So which means the right hand side of this equation is even, but this one is odd. Why? Because you get p squared is odd plus q squared is odd, the sum of them must be even. Okay, so but here we have a product, we have odd is multiplied by odd, which is odd, so which means even plus odd is going to give us odd, but we have odd equals even, which is impossible, which means no solution on this assumption when you have p q are odd. So which means only the solution that we found is p equals 2 and q equals 2. Okay, so I have ended this video. Thank you for watching. I will see you next video. Bye.